This is the 23rd video in a series that I'm making for a course in elementary number theory. And today is a big day. We're going to prove quadratic reciprocity, which is a very beautiful result. Some people say it's the most beautiful result in all of elementary number theory. But before we do that, we first need to recall a couple of things and then also prove some preparatory results that are a bit technical. So let's first recall the Legendre symbol. So if p is an odd prime and a is an integer not divisible by p, then we define this symbol here. Maybe we'll say a by p. It is not a fraction, I should say that. This entire symbol involves the line and the parentheses. So a by p is defined to be 1 if a is a quadratic residue mod p. In other words, it's a perfect square mod p. So it's congruent to b squared for some b. And we define a by p to be -1 if it's a quadratic non-residue. So in other words, it is not a perfect square mod p. And generally, we're only talking about this object right here when a is not divisible by p. But in the case that a is divisible by p, we define a by p, or this Legendre symbol, to be equal to 0. Okay, so our first result, which is a bit technical, and it's not a result that you would really use on its own, it's really used to prove quadratic reciprocity, is called Gauss's lemma. And it's called Gauss's lemma. Well, obviously it's from Gauss, and quadratic reciprocity is also from Gauss. Okay, so we want to let p be an odd prime that does not divide a, and then we'll define n to be the number of quadratic residues from the list a, 2a, 3a, all the way up to p minus 1 over 2a, whose remainder when divided by p is greater than p over 2. Then a by p is equal to -1 to the n. So like I said, this is a bit technical, but it will be useful in our eventual proof of quadratic reciprocity. Okay, so let's get to the proof. So we're going to start by taking the remainders of a, 2a, all the way up to p minus 1 over 2 times a, and we're going to split into two sets. So the first set, which I'll denote by R1, R2, all the way up to Rn, that'll be those that are greater than p over 2. Okay, so notice I'm using an index here that's ending at n. That's because that's exactly how n is defined. And then we'll define all of the rest of them, S1, S2, up to Sm, will be those less than p over 2. Now notice that p is an odd prime, so it's impossible to have a remainder exactly equal to p over 2. Now let's make a couple of quick observations, which will be extremely helpful as we move forward in this proof. Notice that m plus n is equal to p minus 1 over 2. Well, why is that? Well, first of all, these two sets are disjoint. It's impossible for a remainder to be simultaneously greater than p over 2 and less than p over 2. And furthermore, because it's impossible to be equal to p over 2, it means that these remainders must all be greater or less than. So we're getting this entire set right here. But how many elements are in this set? Well, it's pretty obvious that there are p minus 1 over 2. Okay, great. Another thing that I want to notice is that we can exchange these remainders R1, R2 up to Rn, which are greater than p over 2, for a set of remainders which is less than p over 2. And we can do that by subtracting them from p. So we'll say that p minus Ri is going to be less than p over 2, and that's going to be true for all I from 1 to n. And just to point this out, they're also going to be greater than 0. Well, why is that? They're greater than 0 because we can't have remainders that are bigger than or equal to p, given that we're dividing by p. They're less than p over 2 because we're subtracting things off that are greater than p over 2. So that's how we get that inequality here. Now let's see where we are. We have a list of p minus 1 over 2 elements that are all less than p over 2. So n of them are of this form, p minus ri, and m of them are of this form. So because m plus n is p minus 1 over 2, like we discussed earlier, and by definition, the s's are less than p over 2, and by construction, the p minus ri are less than p over 2. So here, together, we have p minus 1 over 2 remainders that are less than p over 2. But how many possible remainders are there that are less than p over 2? Well, there are exactly p minus 1 over 2. So in fact, what we want to show from here is that this represents all possible remainders less than p over 2. And we can do that if we can prove the following claim. And that is p minus ri is not equal to sj for all I equals j. So if these things are not equal, then that means we have p minus 1 over 2 numbers that are between 1 and p over 2. That means we've written all numbers between 1 and p minus 1 over 2 in one of these lists right here, which I've squared in yellow. Okay, so now we want to prove this claim real quick, and we'll do this by way of contradiction. So by way of contradiction, let's suppose that p minus ri is equal to sj for some I and j. Okay, but notice that means that ri plus sj is congruent to 0 mod p. Well, it's in fact equal to p, but p is congruent to 0 mod p, so we're good there. Okay, but now let's also notice by our definition of ri and sj, these guys are congruent to people on this list up here, right? Well, they're the remainders from the elements on this list after dividing by p, but that's an alternative definition of congruence modulo p. So let's maybe reiterate that here. This guy right here is congruent to a times k, and this guy right here is congruent to a times l, where k and l run between 1 and p minus 1 over 2. That's just by the way that we got these two lists of r's and s's. Okay, so now we can factor an a out of this, and we'll see that we have a times k plus l is congruent to 0 modulo p. Okay, but then a is not congruent to 0 mod p. Well, that's because p does not divide a. So that means we can eliminate a from the left-hand side of the equation, maybe by multiplying by the modular inverse. And we see that k plus l is 0 mod p. But that means k plus l is a multiple of p, but that's indeed impossible. And why is that impossible? Well, because k and l both come from the list 1 up to p minus 1 over 2, meaning k plus l is between 2 and p minus 1. But there are no multiples of p between 2 and p minus 1. So just to reiterate, this is impossible. But this being impossible means that this assumption right here was impossible, but that means that this claim has been proven. In other words, everything on this list right here, which is squared in yellow, is incongruent to everything on this list, which is squared in yellow. Okay, so now that we've got that taken care of, let's move on to the next step. So on the last board, we brought into existence these numbers Ri and Sj, which were the remainders of the numbers from this list after dividing by p. The Ri's were greater than p over 2, and the Sj's were less than p over 2. Then we exchange the Ri's for p minus Ri to put them less than p over 2. we showed that everything on this list, P minus Ri, is incongruent to everything on this list of Sj's modulo P. In other words, they're actually non-equal, not just incongruent. But that means we've got a list of P minus 1 over 2 numbers that are all different, and they're all between 1 and P minus 1 over 2. That means this set right here is exactly this set right here. There's no overcounting even. Okay, so what we're going to do from here is take the product of everything in this set, which is the same as the product of everything in this set. So we've got 1 times 2 times 3 all the way up to times P minus 1 over 2 will be the same thing as P minus R1 times P minus R2 all the way up to P minus Rn times S1 all the way up to Sm. Now we'll exchange this equality for congruence modulo P. Notice we'll pick up a minus sign for all of these guys that are in the form of P minus Ri. So that means we'll pick up a total of minus 1 to the n minus signs. And then we'll be left with the product R1 up to Rn and S1 up to Sm. Okay. But now let's recall that R's and S's were defined to be remainders of this list after dividing by P. So we can exchange this product of R's and S's with just the product of this list. That's pretty much the definition of congruence mod P. Let's go ahead and add the fact here that we're working mod P. So that means we have this is congruent to -1 to the n, and then we have a times 2a times 3a all the way up to P minus 1 over 2 times a modulo P. Okay, now what are we going to do from here? Well, from here, we're going to cancel some stuff on both sides of the equation. So let's first cancel the 2 here with the 2 here. We're allowed to do that because 2 is relatively prime to P, and so it has a modular inverse. And then we'll cancel the 3 here and the 3 here, and all the way up to the P minus 1 over 2 here and the P minus 1 over 2 here. So again, that's because all of those are relatively prime to P. That's going to give us a new congruence. So that's going to give us 1 on the left-hand side and then something a little bit more complicated on the right-hand side. So we'll have 1 is congruent to -1 to the n, and then a to the P minus 1 over 2 modulo P. Okay. But now we can rewrite that a little bit, and we'll have a to the P minus 1 over 2 is congruent to -1 to the n mod P. So that's just by moving this -1 to the n to the other side of the equation. But now let's recall from Euler's criterion, we know this a to the P minus 1 over 2 is also congruent to the Legendre symbol a by P mod P. Okay. So stringing the result that we just built right here, along with the result from the previous video, which was Euler's criterion together, we see that a by P is exactly equal to this -1 to the n, which was exactly what we wanted to show here. Okay, so let's get rid of this, and then we're going to move towards our proof of quadratic reciprocity. Okay, we've got another pretty technical result that is going to help us, again, like I've been saying, prove quadratic reciprocity. So here we're starting with an odd prime P, kind of like normal, and then an integer a that is relatively prime to twice P. So in other words, it's odd and it's not divisible by P. Then we have the Legendre symbol a by P is equal to -1 to the t, where t is this crazy object over here. So it's the sum as j goes from 1 to P minus 1 over 2 of the floor of j times a over P. And you'll see that we'll actually get a nice corollary of this at the end if we set a equal to 2, but we're going to present that as a corollary kind of free of this theorem. Okay. So before we get going with the proof, even though I've written proof here, let's do a little bit of an example of this thing happening. So let's say our prime P is equal to 7 and our integer a is equal to 5. Okay, well now let's calculate this number t. So that's going to be the sum as j goes from 1 up to 7 minus 1 over 2. So that's 1 to 3. And then we'll have the floor of 5j over 7. Okay, but notice that's going to be equal to the floor of 5 over 7 plus the floor of 10 over 7 plus the floor of 15 over 7, just as we move through the values of j equals 1, 2, and 3. But notice that 5 over 7 is not 1, so the floor is 0. And then here the floor is 1, here the floor is 2, so in the end we get 3. Okay, well that tells us that 5 by 7, the Legendre symbol, is equal to minus 1 to the 3, which is minus 1. And in the previous video, we looked at all of the quadratic residues mod 7, and we saw that 5 was not a quadratic residue mod 7, which means we should expect the Legendre symbol to give us minus 1. So all of this checks out. Okay, let's get rid of this example, and then we'll dive into the proof. Okay, now we're ready to dive into the proof. And I want to point out that we're going to use our notation of RIs and SKs from the last proof. I didn't want to use a J here because I've used my J as a indexing on that sum. So it's a little bit heinous. And now I want to relate these remainders, recall these were remainders, with this floor object up here. And these floor objects are in fact the quotients. So let's maybe just observe that real quick. So if we take A and divide it by P with quotient and remainder, the quotient will be the floor of A by P. And then the remainder will be one of these RIs or SKs. We don't know if it's going to be an RI or an SK. That just depends on its size. Remember how that we define those. And then similarly, 2a will be equal to the floor of 2a over p times p plus, again, one of the RIs or SKs. We don't know which one it's going to be. But this is all happening in general. So if we take the number j times a and divide it by p with quotient and remainder, we'll get the floor of j times a over p times p plus, and like I said before, one of the RIs or the SKs, depending on the size of the remainder. Okay, great. But now, essentially what we'll do is sum these objects right here. So let's take the sum as j goes from 1 up to p minus 1 over 2 of j times a, and then split it up like this. So notice that's going to give us p times the sum as j goes from 1 to p minus 1 over 2 of this floor object, which is good because that's built into our statement of our theorem here. And then we'll have all possible remainders. And we know we have all possible remainders because we're summing over all of these guys right here. So I'll write this as the sum as I goes from 1 up to n of Ri, and then plus the sum as k goes from 1 up to m of Sk. And then just to reiterate what's happening here, or just to really underscore it, this thing right here, which I'm boxing in this peach color, is exactly equal to our value t. So now I'm going to take this object and sum it a different way. So I'll start by factoring an a out of this thing. That'll give me a times the sum as j goes from 1 up to p minus 1 over 2 of j. But then let's also recall that all of the j's between 1 and p minus 1 were able to be exhibited by the s's and the p minus r's. So that means we can take this and write it as a times the quantity, the sum as I goes from 1 up to n of p minus ri, plus the sum as k goes from 1 up to m of sk. Okay, Again, that's because everything in the list 1 to p minus 1 over 2 was either p minus ri or it was one of the sk's. And now from here, we'll link the equality of these two objects and then work towards the end. But we're running out of room, so I'll bring this equality of this thing here and this thing here up, and then we'll finish it off. Okay, on the last board, we motivated the following equation. So we've got PT, the sum of the RIs, the sum of the SKs is equal to A times NP minus the sum of the RIs plus the sum of the SKs. Now we're going to shuffle some things around a little bit. So I'll start by adding exactly one sum of the RIs to both sides of this equation. So I've got the sum as I goes from 1 to n of RI. I need to do that to both sides of the equation. So that turns this into a 2, like that. And then I'll also subtract the sum of the SKs from both sides of the equation. So I'll here have this as minus the sum as k goes from 1 up to m of sk. Okay, and then that's going to cancel this guy out because we've just subtracted it over. Okay, so let's see what that leaves us with. That leaves us with p times t plus 2 times the sum as I goes from 1 up to n of ri is equal to a times n times p. That's from that right there. And then we'll go from having negative a sums of rj's to negative a plus 1 sums of rj's. And then distributing this a through, keeping in mind of these signs and these additional components that we've added on, we'll have plus a minus 1 times the quantity, the sum as I goes from 1 up to n of minus ri, and then plus the sum as k goes from 1 up to m of sk, like that. And now here's another bit of a trick, is we'll take this a times n times p and change it into n times p plus a minus 1 times n times p. And that may not seem super helpful, but now we can take this a minus 1 times n times p and reinsert it into this sum. So let's see what that'll leave us with. Now we'll have n times p plus a minus 1 times the quantity, the sum as I goes from 1 up to n of p minus ri plus the sum as k goes from 1 up to m of sk, where I just took each of these np's and put it in each of these terms from this sum. Okay, great. But now we can see that this thing right here is exactly the sum as j goes from 1 up to p minus 1 over 2 of j. It's a triangular number. And that's by this argument that we've used several times so far, that p minus ri and sk build up all of the numbers between 1 and p minus 1 over 2. Okay, but like I said, that's a triangular number, and there's a standard formula for a triangular number. That's going to give us p minus 1 over 2 times p minus 1 over 2 plus 1, which is p plus 1 over 2, all over 2. But notice that simplifies pretty easily to p squared minus 1 over 8. Okay, so now we're like honing in on the end of this argument. Let's maybe make sure that we combine this a minus 1 with this p squared minus 1 over 8, and then rewrite this entire thing just to like see what's going on here. We have all of this stuff to the left hand of the purple as maybe our simplified equation. So let's start the next board with that. Okay, we did a bunch of tricky calculation on the last board, but reorganizing that thing that we ended with will give us the following equation. So we've got a minus 1 times p squared minus 1 over 8 is equal to p times t minus n plus 2 times the sum of these remainders Ri. Okay, so from here what we want to do is reduce this thing mod 2. And we'll see that reducing mod 2 will send this bit to 0 because it's obviously even. And that will mean that the right-hand side is congruent to t minus n modulo 2. Notice that I was able to get rid of the p because p is an odd prime, so it's congruent to 1 mod 2. Now let's also notice something else. In our current setup, a is odd, but that means that a minus 1 is even. In other words, a minus 1 is congruent to 0 mod 2. So that means this entire left-hand side is congruent to 0 mod 2. So that means we have t minus n is congruent to 0 mod 2. In other words, t is congruent to n mod 2. But if t is congruent to n mod 2, then that means minus 1 to the t is the same thing as minus 1 to the n. But let's recall that the n was exactly the n as defined in Gauss's lemma. So that means minus 1 to the n is equal to our Legendre symbol a by p. And so that finishes the proof of this theorem. And now I'm going to erase this theorem, add a corollary, and this bottom part, but I'm going to leave this calculation that we ended with because this calculation will actually help us prove a nice corollary. So like I said, now we're going to look at a corollary, not exactly to the last theorem, but to some calculations in the last theorem. So recall that calculations from the last theorem brought us to this stage right here. And this stage did not depend on a being even or odd. So now we'll set a equal to 2, and that'll allow us to produce the following result. So the Legendre symbol 2 by p is equal to minus 1 to the p squared minus 1 over 8, which is 1 if p is plus or minus 1 mod 8, and negative 1 is if p is plus or minus 3 mod 8. Now, I should have maybe said this before, but this looks a little worrisome because it looks like it might be a rational number. But in fact, it's not too hard to check that if p is an odd prime, then p squared minus 1 over 8 is a natural number. Okay, so just to reiterate where we were before, we had a minus 1 times p squared minus 1 over 8 is congruent to t minus n mod 2. But now notice if we set a equal to 2 right here, then a couple of things happen. So this one thing, which I'll leave as a homework exercise, and that is t becomes 0. That's because all those floors are equal to 0. That's actually not too hard to check, but I'll leave it to you guys to check that. So t is equal to 0, which means we have n is congruent to p squared minus 1 over 8 mod 2. Remember, n is congruent to minus n mod 2. That's how we can forget about that minus sign. Okay, but then by Gauss's lemma, we know that minus 1 to the n is equal to the Legendre symbol 2 by p, given the fact that we have a is equal to 2 here. But then by this congruence mod 2, we have that is minus 1 to the p squared minus 1 over 8. And then where do you go from here? Well, if p is plus or minus 1 mod 8, then this exponent here is even. That's easy to check just with basic arithmetic. And thus you'll get minus 1 to an even power, which is 1. And then if p is plus or minus 3 mod 8, then this exponent here is odd, and you'll get minus 1. And so again, that's just easy to check by arithmetic. Okay, so now that we've got all of these preparatory results, including this bonus corollary, which tells us when 2 is a perfect square mod p, we're ready to prove Gauss's theorem of quadratic reciprocity. Now we have all of the tools necessary in order to prove the main result of this video, and in fact, maybe the main result of the course up to this point, and that is quadratic reciprocity. So if p and q are distinct odd primes, then the Legendre symbol p by q times the Legendre symbol q by p is equal to -1 to the p minus 1 over 2 times q minus 1 over 2. But notice that's equal to 1 if p or q is congruent to 1 mod p. And that's because if one of these is congruent to 1 mod p, then the corresponding fraction over here reduces to an even integer. Thus, you've got -1 to an even integer. And then it's -1 if p and q are 3 mod p. That's because that makes the reduction of each of these fractions to an odd integer. Now, before we get going into the proof, I want to maybe motivate a little bit of this notation, which seems pretty confusing because it looks like a fraction. But notice quadratic reciprocity tells us that the product of these two things that look like fractions, p by q, q by p, is plus or minus 1. So in other words, they almost cancel each other. And that explains this fraction notation. So if they were fractions, then this would always multiply that out to 1. Okay, so let's maybe get into the proof. And this is a nice like combinatorial argument. So we're going to start by considering the following set of lattice points in the plane. So it's going to be all points x, y in z cross z satisfying the following requirements. So x is between 1 and p minus 1 over 2, and y is between 1 and q minus 1 over 2. Okay, nice. So let's sketch up a little bit of a picture of our set S, which we'll be able to use just as reference throughout this proof. Okay, so here's like our x-axis, here's like our y-axis. And we'll want points here from 1, 2, 3, all the way up to this point right here, which is p minus 1 over 2. So we've got 1, 2, 3 here. Then along the y-axis, we'll want 1, 2, 3, all the way up to q minus 1 over 2. And so we want all lattice points that are in the intersection here. So we'll want like this point right here, that would be like the point 1, 1. This would be like the point 2, 1, 3, 1, all the way up to p minus 1 over 2, 1. And then we'll want this one right here, this one right here, this one right here, 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 and then up here, here, here. And then our upper right point will be this point, p minus 1 over 2, comma, q minus 1 over 2. And let's point out really quickly that these are all filled in. Okay, great. And from here, we're going to split S into two pieces. So I'll call it S1 union S2, and I'll put a little dot there because this will in fact be a disjoint union by construction. So we'll say S1 is all points x, y satisfying the following inequality. We have q times x is less than or is bigger than p times y. And then S2 is going to be all of the other points. So S2 is equal to all of the points x, y, where qx is less than py. So it's pretty clear that those are disjoint because it's impossible to have this greater than and this less than condition at the same time. You might say, well, how do we know that this forms everything from S? Well, that's clear because P and Q are distinct odd primes, and we're taking X and Y up only to this place, P minus 1 over 2 and Q minus 1 over 2. So it's impossible to have a multiple of P and Q kind of in this space. Now from here, we want to build out our sets S1 and S2 into things that look like objects from our previous preparatory lemmas and theorems. And we can do that as follows. So we can take Qx over P, and notice that that is always less than or equal to q times p minus 1 over 2 times p. Well, that's because x is less than or equal to p minus 1 over p. That's pretty clear. But now that is going to be strictly less than q over 2. And that's because p minus 1 over p is strictly less than 1. Okay, so now let's summarize all of that with the following floor inequality. So we've got the floor of q times x over p is less than or equal to q minus 1 over 2. Okay, well, so if qx over p is strictly less than q over 2, then when we take the floor, we can subtract a little bit from this right side and then also change the strict inequality to a looser inequality. Okay, and then we'll have a similar inequality involving the p's. So we'll have py over q is less than or equal to p minus 1 over 2. And that's from essentially the same argument here where we just replaced p with q. Okay, so let's move these inequalities over here, and then we'll use them to re-describe our sets S1 and S2. Okay, so we just produced the following inequalities, which will allow us to rewrite our sets S1 and S2 into a method that's a little more advantageous to use our previous results. So now notice that S1 can be described as all lattice points x, y satisfying the following inequalities. So 1 is less than or equal to x, which is less than or equal to p minus 1 over 2. So we're allowed to take all values of x, but now y goes between 1 and the floor of qx over p. Great. And so that follows from this guy right here because the floor of qx over p is less than or equal to q minus 1. Okay, great. And so now we can do a similar rewriting of S2. So let's do that. So we've got S2 is equal to all lattice points x, y satisfying 1 is less than or equal to y, which is less than or equal to q minus 1 over 2, and 1 is less than or equal to x, which is less than or equal to the floor of py over q. Okay, great. And now these floors of qx over p and py over q look a lot like the objects from our previous work. Okay, nice. So now let's measure the amount of elements in S1 and S2. So let's notice that S1 has the following number of elements. So we've got the sum as j goes from 1 up to p minus 1 over 2. And then for each x value, we'll have this number of y values contributing. So we've got q times j over p. So the floor of qj over p. So I'll call that t sub 1 because we used t as a representation of this type of number in a previous proof. And then similarly, we'll have the number of elements in S2 is equal to this sum as j goes from 1 up to q minus 1 over 2 of the floor of pj over q. And I'll call that T2. Okay, so now we've got all of our stuff built and we're ready to finish this proof. So we took our set S and broke it into two disjoint pieces, S1 and S2. Just for an idea of the geometry here, if we put the line py equals qx through the plane, we argued that it won't go through any of our lattice points, and everything below that line will be S1, and everything above that line will be S2. So that's what I've drawn here in the picture. Furthermore, we had the size of S1 was T1, the size of S2 was something we called T2, and those T1s and T2s were defined as in a previous theorem. So that's going to show up when we finish this thing off. Another thing that we can notice is that the size of S is pretty easy to calculate. It's just P minus 1 over 2 times Q minus 1 over 2, because we've got freedom of choice in these x and y's from 1 to P minus 1 over 2 and 1 to Q minus 1 over 2. Okay, now we're ready to finish it off. So now we've got our Legendre symbol P by Q times our Legendre symbol Q by P is equal to -1 to the T1, because that's how T1 was defined as in the previous theorem. That will be this P by Q. And then -1 to the T2, and that'll be this Legendre symbol Q by P, again, by that previous theorem. But now, notice that that's equal to -1 to the T1 plus T2. But that's -1 to the size of the whole set S. So that's -1 to the P minus 1 over 2 times Q minus 1 over 2. But check it out. That's exactly what we wanted to show over here. And then this equality to this part right here follows very, very quickly. And I don't know that we really need to write that down. If you're a little bit unsure of the details here, you can just break this into cases. Let's say if P is 4K plus 1 or Q is 4K plus 1, that would be one case. Or if P is equal to 4K plus 3 and Q is equal to 4L plus 3. That would be of the form 1 mod 4 or 3 mod 4. And then you'll see that we get this result pretty quickly. Okay, so that finishes this proof. Okay, so that was a big video of just pure results. So I'll make another companion video to this where we look at a lot of examples of quadratic reciprocity type calculations. And that's a good place to stop.